So your exam is next Tuesday. This is the review. You will notice it is 50 questions. That's just because I wanted to give you plenty of chances to practice the more challenging content. You will notice there's not a lot of questions of the stuff that I kind of expect you to know how to do without much of a review. And then there's several questions of the stuff that I know you're gonna have to remember or relearn all over again how to do it. The exam itself, though, will only be about 20 questions. It is not open notes, never will be. It is written by me, it's on paper, and you will get partial credit based on how much your answer is going in the right direction. So if you're one of those that does it all in your head and then puts the answer on the paper, that's probably not a good thing. Maybe start getting in the habit of trying to show a little work along the way, because then I can give you partial credit. If your answer was wrong, but your work was right, and maybe you had a sign error or something. So far in the review, you should be able to do 1 through 14. Don't let these fractions that are in the exponents here for 13 and 14 throw you off, or in 10. Pretend like they were plain old whole numbers. You should know what to do, whether you're multiplying or adding them, and then just go to your calculator and type the fractions in. So like number 14, that's just multiplying. The 2 exponent times, I think that's 5/3. So that would be p to the 10³ power. I'm going to teach 15 through 18 on Thursday and Friday. Friday's lesson, you will get the video posted, and then you'll be able to go in and watch it and fill in the notes. Okay. Okay, as I was saying, you should be able to do 19 through 30 on this page completely. You should be able to do 31 through 36 completely. You really should be able to do 37 through 42. Well, maybe through 40. That's just solving equations, but I am going to refresh you on that on Thursday. Number 37 would be by factoring. 38, I don't know off the top of my head if that's factorable or would be quadratic formula. 39 and 40 are just multi-step, then solve. Those are just linear. There's no exponents. 41 and 42 are literal equations. You're just, think of it as a cup game. You're shuffling the variables to get the one they want by itself. Enter the next page. This is rational expressions. Then at the bottom are radical expressions. We are going to cover rationals today and tomorrow because they are the most challenging ones. I think that was it, right? Yeah. Okay. So you've got the exam review in your hands. The answers to the exam review are not a secret, okay? I'm going to post them. I'm not going to post them yet. I will probably post it Friday morning so that when you finish the notes that are going to be recorded for you on Friday, you'll go to your exam review and you'll have the solutions posted in Google Classroom. You'll have the solutions and like me working it out. It's all going to be there. This is not a grade. I'm not taking a grade on it. But you know, this is how you study for math. So between now and next Monday night, you need to go through each section of questions and just make sure you know how to do it. Try a few, check your answers, and if you're getting it wrong, come to me. Okay, especially flex. If you're not work-based, you can come to my flex. Gotta pass, so let me know ahead of time. Okay, so if you'll put that away. Let's see, who all, we can only have exactly enough. Mason, Haley, Mallory. So I have one extra. I need to stop copying. I've been copying 25 because I keep forgetting there's actually 24 of y'all in here. All right. Oh, she responded. She said, "Thank you. Me too. Have a good day." Rational expressions. What prefix do you hear in the word rational? What's the prefix word that you hear? Ratio. What is a ratio? Starts with an F. It's not the letters. Fraction. Ratio is a fraction. It is a comparison of two numbers. We're dealing with rational expressions, which means we are taking the two numbers and we're putting them in a fraction, a quotient, meaning dividing. Start simple. 2 over 3x is a rational expression. 3 over x minus 5 is rational. Those are commas, by the way. They look like floating exponents. I just noticed. That's a comma right there, and that's a comma. Yeah. Anyways, and then more complicated, x squared minus 4 over x squared minus x plus 5. That's a rational expression. We've got to cover stating the domain of a rational expression, simplifying them, adding and subtracting, multiplying and dividing. That's what we're doing between today and tomorrow. Today we're going to cover stating the domain, simplifying, and multiplying and dividing. Because adding and subtracting is where it's more challenging. And you may remember why, because when you add and subtract fractions, you got to have common denominators, and that's where it starts to get sticky. Okay, so going back to just understanding that a rational expression is a fraction, there is a restriction or a rule, if you will. There is a rule in math with fractions. What's the rule? You should know it. You cannot divide by 0. That's the rule in math. So if I'm asking you what's the domain of this rational expression, there is some type of number or numbers that would make the bottom 0, and those would need to be off limits because you, say it again, you said it, you can't divide by 0. And if you ever forget that, just remember that it's okay to have 0 in the top of a fraction, but it is no-go to have 0 in the bottom of a fraction, right? So let's make a note right here. What's the restriction? With rational expressions, you cannot divide by 0. You can't do it. So then I want you to write, no. No, can't do it. Maybe even go to a red pen or something and be like, no, can't do that. So to identify the domain of a rational expression, you have to find out what makes the bottom 0, so then you know that that's off limits. Okay. First, let's refresh you what domain means. Domain is the set of all real numbers where x is defined on the graph. Remember, domain refers to what? X. The x values. Not the y values, the x values. The y values are called the range. Domain is the x, range is the y. Let's start really simple. Here's an example. Remember what I said before, when you're trying to understand a challenging concept, put it on a very simple elementary level and wrap your mind around it, then apply it to the harder concepts. Let's say you have some funky graph like this. Trying to strategically make that an open circle. Okay, so let's say you have some little funky graph like this where it is a segment connecting the point 1, 1 to the point 3, 1. This is definitely closed. This is definitely open. Okay, if I said to you, now we're not going to have any graphs like this. I'm just trying to help you understand what domain is. If I said to you, what's the domain here? I'm asking you to tell me, what are the x values covered by the graph? What x values, if I was to list in a T-chart all the points on that little graph, clearly I'd start with 1, 1, right? And your mind might think, oh, 2, 1, and then 3, 1, except that's what type of circle? Open. Now, would that be all of them? No. What did I tell you that day? You've got how many points between any two points? Infinite. So, if you were to sit and list the nice pretty numbers, you've completely skipped, like, 1 1/2 is in there. 1 3/4 is in there. So, we can't do this. We can't list the entire T-chart from a graph because it's not possible. So that's where, think back to last week, interval notation comes in. We cannot list it because we'd be here forever. It's not possible. But we can write an interval that represents it. And you're only focusing on the x values. So here you would say that the domain is, now there's two ways to write it. I'm going to show you. It's all the numbers x such that, and you translate that to an interval. That's running from 1 to 3, but open on 3. So it's in between 1 and 3, and when it's in between, we said they always face like this, and it's closed on 1, open on 3. You can say that. Or, if you prefer interval notation, which is the method I prefer, you are writing that the domain is from 1 to 3, bracket on the 1, parenthesis on 3. So, pick which method you like and run with it. Now, that was stating the domain of a simple little segment. We don't have segments, we have rational expressions, which means we have to keep in mind what is the rule in math with fractions. Y'all are going to get tired of saying this, but I'm hoping to train your brain to think this way. What's the rule in math with fractions? You can't divide by 0. So that means focus your attention on the bottom and see what makes it 0. So let's go to the next page. That was me just saying preview of what's to come. Focus here. Okay, let's start simple. Practice. We're going to start with rational expressions that do not factor or simplify. Like we're starting with basic ones that are already in simplest form, so we can discuss the domain. Find the domain of 2 over x minus 3. Okay, so here are your steps to finding domain. Here's your steps. Step 1, which we are not doing here, and I just told you why, is simplify the expression. I guess we could have just left it at simplify, but simplify it. The top will factor out, bottom will factor it out. And the reason why is because, and this is going to happen in a little bit, because check for common factors that cancel. You're going to check for common factors that cancel. We will have an example where that happens, just not yet. That's more of like example 4 or 5. If you have one, a common factor on top and bottom, and they cancel, that's called a hole. It's a hole in there. It's called a hole. I'll put in parentheses after that, hole in graph. I will let you know when we have an example like that. After you simplify it completely, you check for anything that will cancel, then you set denominator equal to 0 and solve. You set the denominator equal to 0 and solve it. You're solving it because you're trying to find out what makes it 0, because then that's off limits. Once you find out what makes it 0, you write the domain. I'm just going to write capital D, the domain, and state what numbers are not allowed. It's not possible to list all the numbers allowed because there's infinite. So instead you say, okay, this would be a lot easier for me to just say, hey, it's any number you want except 3. Why is it not 3 in this one? Because if I had a 3 right there, what would end up on bottom? A 0. So here we go. Nothing factors here. So I'm going to circle a 2 like I'm at step 2, if that makes sense. So x minus 3 equals 0. Solve. Add 3 to the right. That is off limits. Hence the reason I just struck through the equal sign. That is off limits. Can't touch this. No, sorry. Too early. That is not allowed to be plugged in here. So now I'm going to state the domain. The domain is all real numbers x such that x cannot be 3. You can say that, or I want you to visualize a number line. So any number is allowed, right? Yeah? Except 3. So I want you to visualize a number line that is entirely shaded except what number? 3. Now, here's what that looks like. Now translate that to interval notation. What was to the left? Negative infinity. What's to the right? Positive infinity. So the interval notation would be negative infinity up to 3, hop, skip, and jump over 3, and then keep going. That's the interval notation for this expression. The number that makes the bottom 0 is called a critical point, because at that number, it is critical that you list it and skip over it and then continue to write what would be shaded. Okay? You will notice that if you draw a number line, just sketch a little number line, your interval notation is directly related to your number line. I have 2 sections of shading, right? So I have 2 intervals to list. Does that make sense? By the way, you would say that, you say the union here, you say union here because you're saying, hey, the numbers that this graph covers on the number line include all of these to the left of 3, and then also it also includes all the numbers above 3, but they don't overlap, so that's why it's a union. Remember, union means just put them together. In the set notation, you could say that x is an element of the reals such that x cannot be 3. You can also list that. So there's multiple ways to see it. You might see me write it that way in the answer key to the test review. So that's why I'm showing you that. But in fact, we probably should train you to do that. Let's try another practice problem. Number 2. All right, let's make it more challenging. We are stating the domain. State the domain. And then here is where factoring is necessary. Look at the top. Does x squared minus 4 factor? Yes. To what? See how easy it is if you can recognize those shortcuts. They're both perfect. The exponent is divisible by 2. 4 is a perfect square. And it's a minus sign. It has to be a minus sign, by the way. If it was a plus sign, the top would not be factorable. Okay, so glad you said that. If you come in here and you cancel that, you're making up new math. Here's why. The x squared on top is attached to what? The minus 4. Plus and minus signs are kind of like chain links. Okay? You cannot go in and separate elements of them. You can only separate the entire expression, or you can only cancel the entire expression. The only things that you can cancel individually have to be surrounded by multiplication. For instance, if you had, say, x squared, I'm just making one up, and then let's say on the bottom you had this. Then there's a GCF on the bottom of x squared. Notice x squared, GCFs with variables, you always take the smallest exponent. So I can pull 2 x squared. I can pull it out of this, this, and this. So this would look like x squared. This would be squared to the 1, and this would be gone, right? Y'all with me? Okay, now look. This is attached by what? Multiplication. This is attached by what? Multiplication. So I could rewrite this terms over to their own fraction. And what is anything divisible by itself? It's a 1. So that's why that cancels. Can't do that here, because if I cancel this out, that's no longer x squared minus 4 on top. Now it's just negative 4. This right here was allowed because when I canceled that out, it did not change the value of the binomial. Does that make sense? And that is a very common mistake. Always check and see, is it part of a polynomial? Because if it's part of a polynomial, you cannot just go in there and take a piece out like that. Okay, so looking at the bottom of this, and this is where I think I've started to teach the fraction method with factoring, is we need to factor that. You do not want to sit here and factor this by grouping when we start getting to the more challenging problems, because you're going to end up with 1, 2, like 3 lines, then we're going to still be over here, and then we're going to have to keep going. So here's where I need you to embrace a shortcut in factoring, and it will help you when we get to the more challenging questions. The first shortcut is if A is 1. Do y'all know it? If A is 1, you can go straight to your parentheses with your binomial. And you probably got told this shortcut last year in Algebra 2. I get nervous teaching that shortcut because I've seen people abuse it. For instance, if there had been like a 3 there, I've seen people ignore that that's a 3 and they go straight to parentheses and then they get it wrong. So you need to know that the only time you can use this shortcut is when the lead coefficient in front of x squared is a 1. Then you can do this. What is the shortcut? It is saying to yourself, what are the factors of negative 5? You still do the a times c, but because a is 1, it doesn't change anything, right? What are the factors of negative 5 that add up to negative 4? Negative 5 and 1, right? Double check it. They do multiply to give you negative 5. They add to give you negative 4. And then you've got x and x. So that's the shortcut there. It is very helpful. Now, do we have any terms that can cancel? No. So we factored this just to practice more factoring and to look at it and to recognize when we cannot cancel. Now what we need to do is state the domain. The domain comes from the denominator. Just think of domain starts with what letter? Somebody. Denominator starts with what letter? Yeah. So just remember the domain, focus on the denominator, okay? After you factor it, check for anything, it'll cancel, but then go to the denominator. When it's in factored form, it's easier. That's another reason why you want it in factored form. This right here, get to a different color. Where's my, there it is. This right here is some crap times some crap, right? Yes? Y'all with me? What's the only way to multiply 2 things together and get 0? One of them has to be 0. It's called the zero product property. Listen to the name of it. The zero product, meaning you multiplied and you got a product of 0. The zero product property states if you're multiplying any 2 things, how ugly they may be, and you know they're going to give you 0, then one of those things at least, or both, has to be the number 0. So you just say to yourself, okay, well then what would make that 0? 5. What would make that 0? -1. So when it's in factored form, if you can get from this to this, you can see the domain restrictions. So my step 2, set this equal to 0. I'm going to do it all out. Do this one all out, and then y'all can start taking corners, shortcuts. Set each equal to 0 and solve. So here, 5, here, -1. And then because those would make it 0, this is where you get to have fun. Slash it, those are off limits. And now you state your domain. Your domain is all real numbers, such that x cannot be -1 or 5. Or you can, instead of the word such that, you can write the word and if you want to. You can say and x cannot be, it's up to you. Interval notation, visualize to yourself the entire number line is shaded, but I have an open circle on -1 and 5. You do have to think of what order here in terms of the numbers. You could write it like this, so it's coming from -infinity, it's going to skip over -1, then it's going to go from -1 to 5, and then it's going to go from 5 to infinity. I don't care which.
I'm good. I understood the interval notation better than the
Set notation?
Yeah.
The set notation is saying that it's any number you want to plug in for x from the real number family. There is a restriction, and that's that you cannot pick -1 or 5. That's how you read that. Level up. Yeah. You don't, good question. You don't repeat such that's in your set notation with the bar. So you could write the word and there if it feels repetitive, but the bar is always the first, where you say such that, and then I either write the word and or I'll do ST. I'm not nitpicky on that though. Just don't do a second bar, because then that doesn't make sense. All right, let's do another one. All right, state the domain. Let's go back to a somewhat simple one. Now the top won't factor, so that's good. What about the bottom? Bless you. Yes. Whenever there's two terms, check first to see if it's a difference of squares, and this is not because the 7's in there. Then check and see if there's a GCF, and there is a GCF. So this is a basic, pull the GCF to the front, and then you're left with a binomial. So we're going to state the domain here. I'm going to write this in factored form. I have a GCF of x, and I'd be left with 7 minus x. Right? Okay, here comes the domain. I'm at step 2 now. Set the denominator equal to 0 and solve. You still have something times something, right? Okay, so that means that you set each of them equal to 0 and solve, and those are your restrictions. So you set x equal to 0, 7 minus x equal to 0, solve. Okay, well that one's done. So restriction. Here, subtract 7, be careful. Then divide by -1. Then if it bothers you, go back and check it. Or just look up at it. 7 minus x. What would make that 0? If x were the number 7. So that's how another way you could look at it. So my domain is any number from the real family with a restriction of can't be 0 or 7. Now in interval notation, I'm going to skip from 0 to 7 and then go to infinity. It's going to come from the left, then it's going to go from 0 to 7, then it's going to go from 7 to infinity. And once again, I don't care which method you use, you just need to understand how to use it. Okay, one more example, and this is where we are going to be able to simplify it first, then state the domain. We will have an example of a hole in the graph and then an asymptote. And you're going to see the difference between what's what. Quite good. Okay, so go to the next example, practice number 4. Here's the problem. Simplify and state domain. Okay, when you first look at it, you got a trinomial on top, a binomial on bottom. The top has a GCF of what? 3. Let's pull it to the front by division. The bottom has a GCF of what? 12. Pull it to the front by division. The 3 and the 12 would be the same thing as if I had some fraction, times 3 over 12. Like if they weren't over there and I said times 3 over 12. 3/12 reduces to what? 1/4. So I can come in here and say, okay, and here's how I do it. I say to myself, oh, that 3 is going to divide away down here to the 12, leaving me with a 4. That's the way I do it. Now, look at your polynomials. So I know I'm going to factor this. I'm going to check. I know that 1/4 is going to be in my final answer. I'm going to have a 4, okay? So I'm kind of just making a note like, okay, when I get down to the end of this, I don't need to forget there was a 4 there. And then also, what do you recognize about this? That's a difference of squares. Please train yourself to find those because, bam, this is x plus 1, x minus 1. I'm done there, right? Now, the top one, we're going to have to factor. Here's where you got to learn how to organize your notes. Let me show you a technique that I use so that I'm not rewriting the entire problem over and over and over. I left space on purpose. I'm going to take that top polynomial and I'm going to work on factoring it right here. What's a times c? Negative 3x squared, it's got to add up to positive 2x. What are the numbers? Negative 1 and 3. Double check it. Right? Okay, so I'm going to rewrite the 3 terms into 4 using that right there. Right? So first term, new terms, last term. Let me color coordinate. I know I'm fixing to lose y'all to the bell. If you don't mind, let me finish this problem because we're almost done. Notice I did not copy plus 2x. That's because I rewrote it. This should be a refresher. We've already been doing this. I call this an aside, like a side note, where I'm working on it and then I'm going to plug it back in. Okay. Let's group it. Group the first 2 and the last 2. What's the GCF here? 3x. What's left? X plus 1. What's the GCF here? Negative 1. What's left? You divide a negative 1 out. And then now, look, I've got too much space. I can go straight to here. What's the new GCF? So we're at the last step. We factored it. It's now completely in factored form. Do you notice right here, x plus 1, x plus 1. Do you see that? You can do that because they're surrounded by parentheses, which is multiplication. If I go in and I cancel that, it's going to, this is supposed to help you remember, it's going to leave a gaping hole in your problem. That's because it's a hole in the graph. Okay? So you would say that in your domain, there is a hole at, and it's whatever would make that 0. What would make that 0? Negative 1. There is a hole at negative 1, and it's because that factor canceled. There is an asymptote, which we've already been doing, right here at positive 1. What would make it 0? Set it equal to 0, add 1, positive 1. There's a whole, an asymptote at x equals 1. So your domain here has 2 restrictions. X can't be negative 1, and it can't be positive 1. And the difference is one's a whole, one's an asymptote. All of the examples we've done before were asymptotes. I just didn't show you that word yet. Does that make sense? You're welcome to pack up now. I'm going to write the domain out. So it's the same concept. I will post in Google Classroom what you can practice. I'm probably going to just pick the ones from the test review so that way you're already kind of starting it. Or I might post an IXL and just say get to like 40 or 50 just to try a few.